Hi, hello. So I'm Csaba Kilai from the Go Ethereum team. I will talk about the Ethereum protocol landscape, the P2P protocol landscape. I'm calling it landscape because depending on who I speak to, I see different views of what's in the P2P protocol. So we have quite a number of complexity in the P2P protocol landscape. We have the EL networking with its discovery, dial, sync, and then the mempool. And then we have the CL networking, which again, it's discovery, dial, sync. And then it does the block diffusion, the attestations, the attestation aggregation, and the block dispersal. And then there's the connection between the two, which is also part of this protocol landscape, I would call, the engine API. So when then this all together should work on top of a number of things. So we have minimum node requirements, we have node heterogeneity, and number of nodes. And then on top of this, we want to scale. Right? So when we scale, any of these could become a bottleneck. And that's a bit of problematic because often we just speak of one of these things and then it seems like super scaling, but then one of the others comes a bottleneck. So let's see a little bit them one by one. So let's start with discovery. Often we think discovery is slow, discovery is finding other peers, and that's sometimes a problem. So we do things about it. We have solutions. We are moving, for example, in the EL from Discovery v4 to Discovery v5, which is faster. And the CL was already starting with v5. Then we have something in Discovery v5, which is called topic search, which we are not even using, and we can enable. And then the last thing about Discovery is that it's actually not slow. So there you can find a link. I was crawling the whole network in 50 seconds. So if you want to find peers, you can find them fast. Then there is dial, connecting other peers, very important in peer-to-peer networks. And if you are working on these clients, you will often notice that you cannot connect because everyone is full. They just don't let you in. So dial is about making dial be possible. And we have a few solutions here. We have problems here, and we have improvements. Problems in the sense that dial is slow, that you see on the top. That's the dial progress. And what you see on the bottom is dial progress after a few changes. So solutions here are kind of changing how we manage the peer pool, separating inbound and outbound peer pool. It's already there in all the clients. And then we have to do things that are typical in peer-to-peer. So you have to drop peers, you have to score peers, and you need kind of protected peer pools for the peers which are actually useful for you. So this is dial. Then there is sync. So syncing means syncing state, syncing the block history. But the important thing about sync is that there are kind of two different use cases. Sync when you are just one node starting up, and that's what I call node sync. And then there is sync when you sync because of some other event, some external catastrophic event, and there is everyone syncing. And the second one is more of a problem. So the node sync is more of a user experience problem, how much time you need to actually be part of the network. Sorry. System sync is instead more of a system-level problem. And it becomes a scaling problem. What if we scale the throughput, and then your system syncs become much heavier, and then we might get into a point that we cannot sync all the clients at the same time. We have ideas here for solutions. So one thing that we can do here is what I call swarming sync. So sync now is done in a way which is just linearly syncing typically. But you can do syncing in a way that the syncing nodes are kind of forming a swarm, kind of BitTorrent swarm, BitTorrent-like. So as it's done there, and there are the standard techniques there, which were developed like 20 years ago, which we can use. So we have to send a sync state, and that's already introduced in the network. This was part of EASE-69 with the block range extension. And then we can add on top of this. We can do peer exchange, we can do peer chunk scheduling, and these can improve sync speed. So we can do things about sync. Okay, so after this starter of 3 different things, let's see what we have next. And let's take a bigger topic, the mempool. So the mempool, first of all, we have to know how the mempool works. and what's in the mempool. So this is a graph, and it's just 1 day of sample, so don't take the percentages like super serious. But this is 1 day of what's going through the mempool. And on the left, you see the ratio of transactions per type. On the right, you see the same weighted by the size of the transaction, so by bytes. So what you see is that obviously blobs are the big ones, and type 2 transactions are the many ones. And then this is another view. This is how many transactions, of all the transactions that will make it to the block, a node is receiving. So this is how many you received of different types. And then we see, oh, we only received 50%, but that's because only 50% was public. So the mempool actually, if I just switch back and forth a little bit, you can see that my node is basically receiving everything that is public through the mempool. This is another view of the same thing. This is a distribution of how many nodes received a given transaction. And what you see, if the transaction itself would be on the left, that would mean it's a transaction which no one received, and I was not putting the 0, I was not putting in this chart the private transactions, because we are not interested in those. Here, from the mempool perspective, I was just putting those that were hitting the mempool. And once a transaction is hitting the mempool, everyone is seeing that transaction. That's what you see on the right. Like, 1 there means everyone has seen the transaction before it was getting into a blob. So we can basically say that our mempool is fully synced currently. This is another view of how the mempool works now. So what you see here, every single line is one specific transaction, and you see the timeline of spreading in the mempool. Down below, what you see is the time before block inclusion. So if you take one example, that was hitting the mempool 12.5 seconds before it was included in the block, and then it was spreading. And in 10 seconds, 85% of the EL networks seen that transaction in the mempool. So it is spreading fast. This is not meant to be fast. Here we are not on the fast path, but it's sufficiently fast. And even for the red ones, for blobs, you see that they are spreading fast. We can show this in another view. Here I was putting everything with a start line of 0. So 0 is when you were hitting the mempool. And then everything is going relatively fast. And then we can look at another view. Here what we see is the blob transactions based on their size. So in a blob transaction, you can have 1 to 6 blobs. And based on size, they are spreading, the bigger ones are spreading slower, but they are spreading quite fast again, like in 2.5 seconds, they are spreading in the mempool. Okay, so this is good, but this is with today's traffic. If we want to scale the mempool, then we have to do things. So today we have this kind of globally synchronized mempool. Tomorrow we have to do something. And here what we can do is we can introduce what we call horizontal sharding. Horizontal meaning that we are sharding by transaction. So this transaction is stored in this part of the mempool, that transaction goes to that part of the mempool. And here we can do sharding based on transaction heads, based on sender address. There are different ideas here. And then we can do something like vertical sharding. Vertical sharding means, and this is specifically for the blobs are already segmented because they are already erasure coded in the mempool, and they are already having KZG proofs on each of these segments. So we can just send individual segments. And then we can do even sampling in the mempool if we do this. So there are two kind of protocol improvement proposals there. I was giving them also numbers. Don't take those seriously. We have to specify them. But we can do things like notifying, change the notifications, adding sender address and nouns. And then we can do horizontal sharding, or we can do partial type C transactions in the mempool, and then we can do the vertical sharding. Okay, and now we finished with the EL. Now we just have the engine API and the CL to go through. So let's see if we can make it. CL block diffusion. So we went through the mempool. The block was generated. This block has to be diffused. And that's a very nice peer-to-peer problem. And this is actually a measurement we did 2 years ago when we were adding more and more blobs. And actually, it was before that, when we wanted to add them. This was still with normal blocks. And we wanted to see kind of how fast they are spreading in the network. And so the curves are different size categories, small blocks, medium blocks, large blocks, if you want, up to 1.5 megabyte compressed. And what you see is the timeline up to 4 seconds and below, after. And you see that kind of with the 1.4 megabytes blocks, the system started to have some issues. Below that, everything is working in time. And also consider that this is not counting like when it was released. So maybe the block was released later and then it was sent. So actually, we are spreading it faster. It's just not sent at good time. So this was okay-ish. But we are improving it. And here I was just putting kind of a low latency peer-to-peer toolbox that we are using. So we have a bunch of techniques here. I'm not going into the details of these. First one is segmentation. This is kind of a basic technique that we are using. When you are sending large messages over a peer-to-peer network, you have the store and forward delay. That is, you have to receive the large message, validate it, and only then you can send it. The way out of that is that you are segmenting the message. You are making each one provable. And then you can reduce this store and forward delay. The second one is scheduling and prioritization. And for this, we develop techniques. There are techniques also in literature. So these are kind of techniques known. We just have to apply them. Is a big word there. So we have to find ways to apply them well. But for scheduling and prioritization, we have techniques. Batch publishing is, for example, sending out intelligently, not sending the copies in the wrong order. Then there is quick transport, which is now mature enough to be introduced, and we are introducing it. And this gives us independent streams and prioritization. Then there is the big question of encoding. So the use of erasure coding as part of the peer-to-peer network. It's again something we are not yet using, but there are many examples how to do it. So we are doing that, and then there are different choices evaluated for the coding that is used, read-summon codes, fountain codes, random linear coding, etc. And then there is network coding. Network coding, again, was developed in 2005, so it's quite long out there. We can eventually use network coding, random linear network coding, to do in-network recoding. Finally, with peer-to-peer networks, there is always the idea of overlay optimizations. We have to take that carefully. It's an easy way to partition the network, actually. But if you do it carefully, you can have performance gains with overlay optimizations, which basically means why would you send the same message over the ocean back and forth many times if you can just send it once? To actually make it happen in a distributed way is not that easy. But you can find optimizations there. OK, so now we central block. We still have our blobs, right? So we have data availability, DORB dispersal, and we have the sampling of data availability, which is DAS. Here, I'm not going too much into the details. We had a post on FurDAS 2 years ago, I think now. Maybe, no, a year ago and a half. And FurDAS, so PDAS is what we are introducing now. FurDAS is a construct which is aiming for 256 blobs. It is doing a two-dimensional erasure coding compared to the one-dimensional erasure coding that we are using in PDAS. It already has many low-latency peer-to-peer elements in it. For example, cell-level messaging. I will speak a little bit about that. I also published an update on this post. So in the meantime, we started to use get blobs. Get blobs is basically passing blobs between the EL and the CL, removing an overhead that we had in the system, which is that the EL client was getting the blobs, and then the CL was getting the same blobs on a different pass. So get blobs is shortcutting that, and there is a proposal to make that a better, tighter integration with notifications flying between DL and CL. And then there are different ways of changing the scheme, basically the 2D erasure coding. Instead of using read-summon to use random linear coding or to use random linear network coding, there are a few options there that you can find in that blog post, and I will definitely not have time to go into that. The part that I want to speak about is what we call cell-level messaging. So cell-level messaging is, if you see it's written there, means that you are not just sending out large messages of columns, like we do today in PDDoS, or entire rows, like we do not do it currently, but you are considering the individual cell as a message. Cell-level messaging is there because it has a bunch of advantages. And here the picture is a bit complex, because depending on where we introduce cell-level messaging, as part of the current PDDoS design, or adding also other things, it has different advantages. But let me start with this first one. So if we introduce it as part of the current PDDoS design, if we introduce it as part of this design, then we are getting basically reduced torrent forward delay, because we are not sending entire columns, but we are sending individual cells. These are already proven, they have their KZG commitments, so we can actually do it. This is not a critical now, because now our columns are small. We have 6 blobs, that's like 12 kilobytes. We don't really want to chop that. But if we would have 70 blobs, then the column starts to be heavy, and then you might want to chop it. So then it becomes critical, or at least speeds up distribution. And then it allows another thing, which is column reconstruction. So now if we are in a situation when someone has half of the blobs and someone else have half of the blobs in their execution layer, and they are getting, the CL clients are getting it from the execution layer, one is sitting there with half of the blobs, and the other is sitting there with half of the part of the blob, half of the column, and they just cannot communicate. They have no way to share this information. So cell-level messaging is one way to actually overcome this. We are developing also other solutions for this, partial messages. Let's see which one we will introduce. But that will overcome this problem. So we would be able to just reconstruct columns on the fly. Then cell-level messaging is also unlocking other things. So if we are also adding row topics, so that means that the CL is communicating not just sending columns, but also sending rows on that 2D structure, then we get a very nice property, which is we can also start reconstructing along the erasure coding that was done in the blobs. If we just have row topics, this just means that we can start to do it. We are reducing the CL load. If you are a full node, a super node, which is having all the columns, you don't have to put in the CPU to actually do all the reconstruction. You can just reconstruct a few rows and start to message those. And you can distribute the load in the network with this. If instead we introduce the 2D read-zone erasure coding in the system, we can do cell-level sampling, and there we are using the cells. Finally, if we are kind of getting to the full picture, we are introducing the 2D read-zone erasure coding and the row topics. Then we get a very important property, actually 2 of them. One is that we don't need supernodes anymore. Every single node will be able to start reconstructing. You are getting cells, and as soon as you are having the cells, you can start reconstructing a single column or a single row, even if you are not a supernode getting half of the columns, as now in PDDoS. And with that, we are getting another important property, which I call availability amplification, which basically means that there are no situations when in the network you have kind of borderline available scenarios, because those are the worst ones for us. In a borderline available scenario, that is 60% of the blob, of the full matrix is available, there would be nodes voting for it, there would be other nodes not voting for it. The block at the end would not pass. But it's inefficient because it was actually available. It's much better for the system if we are repairing it and everyone can attest, and then the block becomes actually part of the chain, rather than doing the work and then throwing it away. So with all this, we can get to a point where we finish our presentation. Thank you, and questions. Thank you.
We don't stay too much time, but if we have a little question.
Yeah, I don't see the hands if there are. So.
Yes? Come.
Just quick. How does diffusion in the execution layer mempool work?
So diffusion in the execution layer mempool is a push-pull. So we are pushing transactions. If they are small, we are pushing them. And we are pushing them to a number of peers. The number is actually the square root of our peers. And we are selecting them with a stable selection. And the stable selection is based on the actual transaction sender address. And we are doing this because we want the nouns not to have nouns gaps. So we are sending it to someone, and then some transaction from the same sender will travel on the same path. Okay. And this is the push. And then there is also the pull part. So for big messages, for blobs, for example, we are pulling. Okay. Which is why I'm saying it's not meant to be fast. It's actually slow, because you have to notify, and then they are pulling. Yep.
Thank you. We don't have no more time, but if you want to ask a question, feel free to.
Thank you.
Thanks.